With these last two examples that we did, you can see where the intuitive definition of being able to draw a graph without lifting your pencil comes into play. The most common types of discontinuities are these types where the two ends don't meet up, and then this type where we have a hole and then a point elsewhere at that spot. The intuitive definition of being able to draw a graph without lifting your pencil is basically coming from the real definition, which means as I travel along the graph, I should always be moving towards the spot where the function is defined and where the output of the function is. If you're always moving towards the spot of where the output is, then your limits are always going to match up with your outputs. Now, what does that mean about functions like these? Let's determine the intervals on which these functions are continuous. Let's take the function 4x squared minus 3x plus 5 equals p of x, and the function n of x, which is equal to sine x. I'm going to graph these and look at how they behave. Let's take a look at the p of x equals 4x squared minus 3x plus 5 first. Most of us know that this is a parabola, and if I zoom out, although it's very, very steep, it doesn't have any place on it where the function's value is not both defined and equal to the limit. So you can travel along this parabola and never have to jump off it in order to draw it. So this parabola is continuous everywhere, meaning it's continuous from x values from negative infinity to positive infinity. It's hard to zoom out enough to actually see x values that are really huge because the parabola gets so steep when you get out to numbers like negative 10,000 and positive 10,000. It becomes an extremely steep parabola, but it does go on forever, both to the left and the right. So this is a continuous function everywhere. Our other function, n of x equal to sine of x, it has this wave pattern. I'm sure you've seen this before. If you notice what's happening, that wave pattern just keeps going and going and going. There's no place where the limit does not exist. And there's no place where the limit not existing, or there's no place where the function value is not the same as the limit. So this is also a function which is continuous everywhere. So there's a lot of functions that are going to be continuous everywhere. In fact, if you recall from last section, in a previous video, we said that in order to find the limit of functions like p of x, specifically polynomials, I could have just plugged in whatever x value we're approaching. That was essentially saying that these polynomial functions are continuous everywhere. So polynomial functions are continuous everywhere. Sine is another function which is continuous everywhere. There's lots and lots of other functions which are continuous everywhere. So what can we say about continuous functions? Well, continuous functions have lots and lots of nice properties. If we have two functions that are both continuous on an interval, so let's say f and g are both continuous functions on an interval I, and c is just some real number. We call it c for constant, and n is a positive integer. Then the following functions are also continuous on I. So if f and g are both continuous, then their sum is going to be continuous. Their difference is going to be continuous. Any constant multiple of f or any constant multiple of g is going to be continuous. Products of f and g, f times g, are going to be continuous on that interval. And also, quotients are going to be continuous as long as the denominator is not 0. If the denominator is 0, then we have issues. So think about what that means for our observation. Well, polynomials, when you add polynomials together, all polynomials are going to be continuous. Taking constant multiples, we're going to be continuous. Products are going to be continuous. And quotients are going to be continuous as long as the denominator is not 0. So we're going to say rational functions are continuous except possibly at the denominator of 0, or except possibly when the denominator is 0. Other properties of continuous functions, well, if we have the same assumptions, it turns out if I take a continuous function to the nth power or the nth root, then that resulting function is continuous. We do have to worry about one thing. When you take an nth root, we require our function value to be positive if n is even, because if we have an even root, like the square root, and we take the square root of a negative number, then we're in the imaginary realm. So we require our function to be positive. So as long as the function is positive, it's going to be continuous for the nth root when n is even. And when n is odd, you don't have to worry about that. Powers are always going to be continuous. And also compositions of two functions are going to be continuous as long as we adjust the intervals correctly. So as long as we have the intervals correctly adjusted so that our inputs and outputs work out, then compositions work as well. With all that being said, what can we say about what functions are continuous? Well, we already saw that polynomial functions are continuous. So any polynomial function is continuous. Any rational function is continuous on its domain. So when you don't have 0 in the denominator, sine is continuous. Cosine is continuous. Any exponential function is continuous as long as our base is above 0. The natural log is continuous on its domain. And then the nth root of x is continuous on its domain. So lots and lots of classes of functions are continuous. Let's take a look at these types of functions and determine where they are continuous. I have copied and pasted these functions into the Word document. So all we have to do with these types of functions is look at the domain So the domain of this rational function is all real numbers, except when the denominator is 0. Now, when the denominator is 0, that means x is equal to 3. That means our function is continuous from negative infinity up to 3, not at 3, but then it picks back up after 3 and goes to positive infinity. So anywhere from negative infinity to 3, and then from 3 to positive infinity, our function is continuous, but not at 3. Let's take a look at g of x. So the problem with square roots is that when we're trying to go into real numbers, we don't want to be square rooting a negative. So the domain has a problem when the thing underneath my square root, specifically the 3x minus 12, is negative or less than 0. And if you solve this, add 12 to both sides, then divide by 3, that means the domain has a problem when x is greater than 4. We can rephrase this to just say that means the domain is when x is greater than or equal to 4. So the domain is fine when you plug in 0 and above into a square root function. So we would say we are continuous on the interval from 4 to infinity, because that's our domain. Now, if you wanted to be more precise, do you say, can we include 4? Well, you could include 4. That's perfectly okay. Some people do and some people don't because of the nature of how 4 hits, because you can't approach 4 from the left because there's nothing in the domain. So some people include 4, some people don't. I'm not going to be super concerned if you include or do not include 4 there. Now, how about tangent? Well, when I think of tangent, I want to think of sine over cosine. So the domain is everywhere except for when the cosine is 0, because we don't want 0 in the denominator. Now, when is cosine x equals 0? Well, when is cosine equal to 0? Cosine is equal to 0 when we are at pi over 2, 3 pi over 2, 5 pi over 2, all of the odd number times pi over 2. Here's how we're going to write it. We're going to write this as, we're going to have k times pi plus pi over 2, all right, where k can be any integer. So what's that mean? Well, we're continuous on all kinds of intervals. Pi over 2 to 3 pi over 2. Then we pick back up after 3 pi over 2 up to 5 pi over 2. And we could just keep this going, 5 pi over 2 to 7 pi over 2. We also could have done it with negatives as well. So if we would have liked to, you could have went from negative pi over 2 up to pi over 2. And you could have went from negative 3 pi over 2 to negative pi over 2. So we're continuous on these intervals everywhere except for when x is some integer times pi plus pi over 2. I would like you all to try these functions here. Determine the intervals on which these functions are continuous. Push pause in this video, and then I will show you how to do these in the next video.